This section is called Programming with Hadoop. So this is actually how to use it. In lecture 2, we talked about sort of conceptually how do you write maps and reduces. This is more focused on what actual interfaces do you implement and how does this interact with the rest of the running system. So there's sort of a tour of the major classes and moving parts of a Hadoop process. So some terminology for MapReduce. Every distributed system has similar terms, but they all define them slightly differently. There's a notion of a whole job that needs to be run, and in Hadoop we call this a job. So this means we've got some piece of code that's a mapper, some piece of code that's a reducer, and some data set that we want this to work over. And this process here is called a job. The job is then broken out into multiple tasks. Each file to be mapped is one or more tasks. The task size tends to be broken up within a file, if possible, on block boundaries. There's also a task for each reduced task that you specify. So you personally set the number of reduced tasks that your job should expect, or else you can use a default. Each of these tasks may be attempted more than once. So you might have multiple attempts to complete the same task. A task might mean reading this particular input file, and if the mapper over that input file crashes halfway through, then it's going to restart that task, possibly on a different machine. And so it's the same task, but a different task attempt. So I think systems like Condor or others actually might use these terms inverted, but this is the nomenclature that we're working with. Word count on 20 files, one job. 20 files to be mapped, at least 20 map tasks, more if these files are larger, and some number of reduced tasks. As I said, if a task crashes, then there will be a second or third or fourth task attempt on that task. Eventually, it will stop attempting a given task. If one particular input is crashing over and over, like say there's a bug in your mapper and so one particular slice of the input triggers a null pointer or something, then eventually that input task will fail. At this point, one of two things can happen. By default, the entire job will fail. It'll say, I couldn't complete one of your tasks. But you could also set a quality factor that you want. So you could say that it is acceptable for my job to succeed if only 99% of my input gets mapped. So if you've got very large data sets, you're working with a terabyte at a time, and you don't care if one or maybe two of your input blocks are abandoned, then you can allow your whole job to continue with the caveat that it'll return, I could only do most of the results. Finally, if we're using that speculative execution that I talked about in the beginning, where we could execute the same mapper multiple times in parallel, then we might see multiple attempts ongoing for a particular task, even if there aren't any failures of those attempts. Eventually, one of those attempts will complete before the others, and the job tracker will just order those bonus attempts to be killed. So here is the 20,000-foot view of how the MapReduce process works. There are three principles here. We've got the client computer off on the left. On the top right is the master node, and then we have one or more slave nodes. In the virtual machine in which we're doing the exercise, all three of these roles are condensed into a single VM, but there are different daemons that are running to fulfill each of these roles. So the client computer, the one where the developer sits, is what's actually submitting the job, and the code starts out there. And you actually run the program on that node. And so your program starts up, and then at some point it gets to a submit job call, at which point your computer will talk to the job tracker node. And then you will negotiate with the job tracker and get yourself into the queue, upload a copy of your own code. And then the job tracker tells all the slave nodes which particular work units they should perform. On the slave node, there are multiple task. There's a task tracker, which is the daemon responsible for managing all the tasks in that node. And there are one or more task instances. So the tasks actually run inside of a separate JVM from the task tracker daemon for the reason that if you somehow manage to crash the JVM, i.e. run at a heap space, etc., then you don't want that node to be unavailable for running tasks from other jobs. So separate processes connected via RPC.
Sorry, there could be multiple task instances reporting to each task tracker?
That's correct. There could be multiple task instances per tracker. There's exactly one tracker per node. But if you have 4 map tasks running concurrently because you have 4 cores in the machine, then you would have 4 separate JVMs running isolated from one another. Are there dedicated master and slave nodes? Yes. The job tracker node is well defined in advance, and its address is published in the configuration file sent to all the slaves.
So, I'm sorry, you said there can be multiple task trackers per node? Or?
There's one task tracker per node. However, that task tracker may be managing multiple task instances. So if you have 4 map tasks per node, then all 4 of them would report back to the single task tracker, who, along with the task trackers on all the other nodes, are reporting back to the single job tracker.
Sorry, and these processes are all running as whom?
These processes are all running as the Hadoop user. So whomever starts the daemon on the node. Typically, you will create a separate user account called Hadoop, much like you make a www user for your web server. And then currently it does not support any sort of user isolation. So all of the actual MapReduce jobs are also run under this user's authority.
You mentioned that there are multiple task instances associated with the task tracker.
Correct.
Now, in terms of the JVM instrumentation, does the task tracker run in its own JVM and each instance run?
Right. As I said, there's multiple task instances. Each of these rectangles represents a separate JVM. So they're all completely isolated so that if a task instance does something really stupid like use up all the RAM, you don't orphan the machine. Because if the task tracker were to crash, then that machine would no longer be running work units. So the single master node is running an instance of the job tracker daemon. And clients are continually sending in these job requests. All these italicized terms are classes, by the way, in Hadoop itself. And then on the slave nodes, we run an instance of the task tracker. And this will fork a separate process per instance. So the jobs themselves are distributed to Hadoop by doing the following. First, we take the jar file that the job is compiled into. You can't run this from a bunch of .class files for your program. You have to assemble all your class files into a single jar. Then you run your jar, and your program will upload its own jar into HDFS. It also writes out the configuration spec for the job into an XML file, which is also placed into HDFS. Then over RPC, your client computer talks to the job tracker and marshals this job object across that contains pointers into HDFS for where the jar file is and where the config file is. So then the job tracker then notifies all the task trackers, download the code from this shared DFS, download the config from this shared DFS, and get initialized. And then the task tracker start accepting work units, which are commands to spawn instances of that jar on a particular set of input files. So distributing a job does not involve distributing data itself, usually. And this is implicit in how we've designed our MapReduce pipeline. We've already loaded all of our data into HDFS in advance. And when we put data into HDFS, when we did an initial put command, we were choosing, or being directed rather, to different nodes for different blocks. So the name node, when you go to the name node and say, I want to open this file and write it, it says, OK, connect to that machine and write it there. And so as you do this for different files, they're all spread mostly homogeneously through the cluster. And then when we start this job tracking, when we start this job, all the different task trackers are continuously asking the job tracker, is there more work? And so the task trackers, and then the job tracker will look at its queue of outstanding files to be processed, and it will say, okay, I know that this file is on your node, so you should use this file and this job specification as your inputs. And then it will run your jar on that file.
I'm sorry. So is one file always guaranteed to be on one node?
No.
Does a file ever span nodes?
The files very commonly span nodes. An individual block is the granularity at which things are available. So a file that is less than the block size will not be split, and so that would be entirely one node. But if you have, say, a 20 gig file, then that would be some 80-odd blocks or 200 blocks or whatever. Those might be spread across all the nodes in the cluster.
So what does locality mean then? If one file spans nodes and longer, can you pass a job off to one node?
Well, you would say if a file spans all the nodes, then you would not process the file start to finish in one shot. You would say, okay, this file is 2 gigs, and if our block size was 128 megs, then that means we've got 20 blocks, right? And so that means that we've got 20 tasks. And so it will say, okay, this node should process this file from offset X to offset Y. This node should process offset Y to offset Z, Z to W, so forth, based on which blocks are already on those nodes.
The positioning of the blocks is done for you. You don't explicitly.
The positioning of the blocks is done for you. To my knowledge, you cannot pin a file to a particular node. It is entirely under the hood.
So, I'm sorry, nearby nodes means rack in the same rack kind of thing?
If possible. So if all of the files which are on your node are already being handled by other nodes, then when your node, when your task tracker goes to the job tracker and says, give me more work, it'll say, okay, well, everything that's already on your node has been accounted for. So we know that you're on the same rack as these 3 nodes, and this guy has that block. So pull that block from him and then process it.
So what happens when my block is on a node which is not available?
Each block is actually on 3 nodes. It was replicated at load-in time. So there are 3 candidates to map everything locally. And if a server in HDFS dies, the name node will detect that and knows which blocks were on that server and uses a replication protocol to rebalance.
Say you want to operate on parts of the data sections contained in time, and the way it ended up with the bar box is that it was split across 2 blocks. But could you beforehand somehow say I want my data segmented into these size units?
So it also has the notion of records, and it will do the right thing if a record spans a block boundary. It will read past the end of a block, for example, to complete its current record, so it won't fragment a record. However, if you want the whole data file processed together, you can tell it to not split a file for processing. It would still be split in the physical layout across multiple machines. However, you could pin all the processing for one file into a particular node. At that point, you should ask yourself why, though, because since the mapper should be processing individual records in isolation of one another, then that suggests that you're not thinking in terms of mappers and reducers as you were intended to.
So if your input data is images, for example, would you have a file that's all the images concatenated together and that each image is a record? Is that the way you...
Yeah, so if you had a lot of images, you would not want them to be individual GIF files or JPEG files spread throughout, because each of those would be what, 100K,
Right,
maybe a meg?
inefficient.
It'd be terribly inefficient, and you might have thousands or tens of thousands or millions of them. So there's a file format called sequence file, which is a packed binary format that allows you to put arbitrary binary data records in there. And so you would probably do and you would do an initial load-in pass where you'd make records where the key would be the file, the original JPEG file name, and the value would be a blob.
Right.
And then you would have, thousands or millions of these blob records in a gigantic sequence file.
Does it have to be one gigantic file, or could you have some number of files? And that's
Again, you can use some number of files if you want, but your performance will be harmed if your files are not actually taking advantage of several blocks each.
basically, yeah.
So you should try to shoot for files north of a gig if you can.
Okay.
If your job is opening 1,000 files, then you might want to rethink how you're putting data in, because chances are you could have just lumped that into 100 files or maybe a few dozen files, because there's no reason to be scared of large files in HDFS. If you've got a large volume of data,
It's like 2009, and you can have more than 2 gigs without bad things happening generally.
I mean, this uses 64-bit IDs through everything. So you can have individual files of 100 gigs, and it would be probably happier with that than a whole bunch of little files.
Okay, sorry, to follow up on that, so how, where does
The understanding of how your file records are split get incorporated here. So if some portion of you know what I'm saying? So when it allocates the jobs, how does it know that it allocated the right part of the file? That it ended, the part that is giving to some map job actually contains
It should be the name of the job to know that.
So the question is, how does it know that it's breaking things up correctly? The key thing here is don't think too hard about this. The point, if you think about it, you've got a really long run. Blocks are 128 megs. So sure, there might be some spillover, right? Your record might actually be 128. Your last record might start at megabyte 127 and then go to 128.2, but it understands when it's reading into the mapper that it needs to go past the end of the block to complete its record.
On our local system, are we doing 3x replication?
Inside the virtual machine, there's no replication.
Okay, so HDFS doesn't require the
No. You can
machines
you'd have twofold, or you could have onefold if you felt like living dangerously. Yeah, you can configure that actually on a per file basis. So
3 virtual machines on your laptop, so you wouldn't have a single point of failure, right?
yeah, absolutely. This man's got it. All right, let's move on. How do we actually set up the configuration to describe one of these jobs? As I said, this is going to get dumped out in an XML file. How do we write that file? So there's this class called jobconf, which is sort of the center, the point that ties all these things together. And it's just a small key value store. The keys are strings. The values are things that get serialized out to strings. So you can set the number of tasks. You can set the name of the mapper class, the name of the reducer class, the list of files or directories you want as your inputs, the directory your output goes, etc. And so you write this out in your client machine, and then that's going to get serialized to XML, injected into HDFS. Then all of the task trackers are going to read that file, pull it back from HDFS, and deserialize back into a jobconf object again, which will then be handed off to several different classes in the system. So anything that implements job configurable can read this jobconf. So your mapper, for example, may have a configure method, which will receive this, and then if you have any custom parameters, for example, when you ran that grep query earlier, there was that query string that needed to be sent to everybody. That was just written out into a job-specific key here, and the value was the regex. Then the mapper itself, in its configure step, handled the jobconf, pulled the regex out because it knows what key it's looking for, and then holds onto that to use in the mapper.
What was still the A there?
Sorry, that's an arbitrary type. You read that as alpha. So you can store sort of any type on the right, so long as it can be stringed. So you can integers, booleans, strings, anything you want if you want to base 64 encode it. So this is sort of a depth-first walkthrough of start to finish running job to getting files back out to HDFS for the output. So begin with the client. We've got this client program running our program in a jar. And we create a new jobconf object. And at very minimum, we have 4 methods that we need to call. We need to call this set mapper class and set reducer class. which will contain the name of the classes that we want to use for our mapper and our reducer. We also have to call this file input format .add input path at least once, because we have to specify some path for input. And if you specify just a file here, that's going to be just a file. If you specify a directory, it'll assume it's a directory full of files and use all of them. And finally, we have to set the output path. So we call this file output format set output path. That tells it all of these reducers are going to open a file and write out its results to that file. So we need to set where that goes. And there's a host of other options we could set as well. We can set the number of reduced tasks here. We could set the input and output format, so on down the line. Eventually, we're going to call this run job or submit job method and pass the job conf object to that. The difference is that run job will block, and your program will wait until the MapReduce job completes, and then you'll keep going. Submit job just posts it to the job tracker's queue and returns a handle to that object that you can use later. So you can poll that object for status, and it will say pending, running, failed, finished, etc. So then you could build your own scheduler over your jobs that you need to run if you wanted. So this job client, still running on the client machine, is responsible for determining where the input splits are. An input split represents the section of the input data that goes to one map task. So an input split is, for a file, it is a file name and a byte range of that file that we want to map. And so it looks at HDFS, looks at all those paths that you specified for inputs, calculates the list of input splits, and uploads all that to the job tracker. The job tracker then, we insert the jar. This is kind of not true. I think that the client actually puts its own jar into the shared location. But the job tracker then manages the run queue. And so the scheduler for jobs is inside the job tracker. And as I said earlier, this can be either a FIFO scheduler, or there's also a system now called the fair scheduler, which has this notion of pools. And each pool is guaranteed a minimum number of cores across your cluster. Well, specifically a minimum number of task slots, which you typically tie very closely to the number of cores you have. So there's these task tracker daemons running all the slave nodes, and they poll for work from the job tracker. So I think it's every 10 seconds, the task tracker sends a heartbeat back to the master, and with that heartbeat, it will specify whether or not it's got free slots. And the master will then send back a response telling it new input splits that it should run. And it also tells it where in HDFS that jar file and that XML file were posted. It downloads them, and then it spawns a separate JVM and runs that jar in there. Something that's a little different here than if you have experience writing MPI programs. If you were to start an MPI program on a cluster, you would run that same program on all the nodes. And you would probably just pass it a different argument on each node. And you would run your own main function. You'd start your program from the beginning, and it would determine its node ID and then follow the correct code path for whatever that node is supposed to be doing. This is different than Hadoop. In Hadoop, your main function and your primary program flow are only running on your client machine. It will then use its own main method when starting the second when starting the separate JVM on the task nodes. And this main method does things like retrieve the XML config and get the job conf in play. And then the only code of yours that it runs there is it creates a new mapper and then runs your map method and creates a new reducer maybe and runs the reduce method.
So after task tracker finishes and requests more work, it's not going to relaunch a JVM and re-request all the job-specific jar.
It will cache the jar locally, so it doesn't have to keep re-downloading the jar. But it will actually start a separate JVM currently for every task.
No, but I mean, once it gets to its number of slots, like 4, it's not going to, that one's done, close it down, and then maybe later start up another one.
Yes, it will. That is currently how it works. It currently is a little wasteful, yes. So starting with Hadoop 0.19, there is JVM reuse. And this allows it to recycle JVMs and eliminate that overhead. But that was a pretty big structural change because in the beginning they just did the simplest thing and then from there. The actual main method that it's running is this task tracker child main. And so this actually sets up the task attempt that I mentioned earlier, reads in the configuration, then it uses something called a task runner. And so the task runner knows which of the input splits this task is supposed to be mapping. So it creates a mapper instance and calls the map method once for each record it retrieves from the input split. The reducer is run in much the same way. The mapper is an interface in Hadoop, and so this is the interface that you must implement. So we have my mapper, implements mapper, and you also typically want to extend another class called MapReduceBase. The mapper interface is actually 3 or 4 different methods, most of which you are uninterested in. So MapReduceBase just implements the uninteresting ones in the default way for you. For example, there's a close method. Also, if you wanted to do configuration, you've got a configure method. This provides an empty configure method, etc. So inside of each of these separate JVMs, it creates one instance of your mapper with using reflection. And this exists in a separate process from all the other instances of your mapper. So a common thing that people ask on the mailing list is, hey, I've created this mapper, and in one of my mappers I set this static field, and in my other mapper I can't read it. And that is intentional. There is no data sharing or communication between the JVMs that is user-directed. So if you set a static field in one mapper, you should not expect your other tasks to pick that up in any synchronous fashion or really at all. The key bit of the mapper interface is this method. This is where you write the method that actually handles some key value input pair. So you have 4 arguments here. The key and the value need no introduction. There's another object called the output collector. And so whereas in the examples I was showing you earlier, I just wrote emit, E-M-I-T, as it turns out, Java has no emit keyword. And since you want to be able to return multiple key value pairs, we can't spell that R-E-T-U-R-N either. So this other object will accept key value pairs to forward along to the reducer. It has a method called collect. Finally, there's this object called reporter, which allows you to report back some statistics back to the job tracker and also gain access to some other pieces of metadata about your job. So these keys and values are marked as writable and writable comparable. And what does that mean? Well, they have their own data marshalling format that they use that does not use Java's native serialization. It's very heavyweight, the native serialization is. And also, when they started this project 2 years ago, it also wasn't particularly stable. So they rolled their own. And what this means is that they have their own box classes that implement the methods to marshal data in and out. So there's one of these for basically every primitive type. Integers have int writable instead of integer. Longs have long writable instead of long. There's also Boolean writable, array writable, and for the reason that I have no idea, we spell string writable T-E-X-T. I don't know why, but it saves typing. But that's the only one that defies the convention. So the values have to all be instances of writable, because we obviously want to marshal values from the mappers to the reducers. The keys must obey a stricter interface called writable comparable, because they must both be writable and comparable. And the reason for that is, as I said, the keys common to a particular reduce task are presented in sorted order, but sorted implies comparable. So we have to implement the comparable interface for key types.
Does it make sense, Aaron, to have also your own writable implementations?
It does make sense to have your own writable implementations. Extremely common paradigm is to author your own for your own higher level structures. You can either do this by composing several of these like int writables together, or you could just write the fields out directly as primitive types and then implement the marshalling yourself using the Java NIO methods. It's very straightforward code to write. There's also a compiler in Hadoop called RCC, which most people don't tend to use, but that provides a DDL if you're interested in taking a look. Something else that's a little quirky about writables that one must keep in mind is that writables are mutable. Unlike the types that come with Java, like string or integer, which once you construct them, their values are fixed, the writable family allows these fields to be updated. So whereas you would usually write, if you're using regular primitive types, you might write a loop like this. In Hadoop, you very often create a single object to hold your intermediate data and run the loop like this. And so something to be careful of. And so this has the advantage of providing cache coherency and eliminating unnecessary garbage collections. The downside here is that you have to be a little more careful. The reducer, by default, will construct a single object of type of the value type. And when you call that reducer's next method, it's actually overwriting that same object internally with the new data and handing the same reference back to you. So if you start storing a few of these in an array, you might later realize that you have an array of a dozen handles to the same object that all have the same internal data. So if you actually plan to buffer any values, you need to do a deep copy yourself. Otherwise, you will lose the data. We've defined this map method. And the map method just takes this key and this value. And where do these come from? We know that there's files that have our data in them, but somehow these data files have to be parsed into records. So this is performed by the input format and record reader duo. So the input files are on HDFS. And when we submitted our job, we divided those files into one or more input splits each. And how we determined how these input splits are created is a function of the input format class. And the input format class says, OK, I know how to read these files, and I know that we can split them on block boundaries. So here's a split for each block boundary. Or it might say, I know that this is a compressed file, and I cannot split a compressed file because gzip doesn't support intermediate restarts. So I will only produce one split for this file. And the input format is also a factory for another object of type record reader. And the record reader actually knows how to read the file and parse out an individual record. So there's a few input formats that come out of the box for you. There's a base class called file input format. This is an abstract class. And if you do not specify the input format, it will use the text input format by default. And the text input format assumes that you just have lines of text. And so it will read everything up to a new line as the value. And the byte offset of that line in the file is the key. And this will do the right thing with respect to splits. So if it sees that the block boundary is here and the new line is over here, it'll keep chugging past the block boundary, read the new line. And then input splits that are not the first know that they need to find the first new line within their split before they start picking up records. When you write output from a MapReduce job, you might have noticed when you were in that example that there was a key, then a tab, then a value, then a new line. That's how it, by default, writes output. So there's this second input format called the key value text input format, which reads in individual lines of text, searches for a tab character, and pulls a key and a value apart from there as strings. So that's how you can easily take the output of one MapReduce job and use that as keys and values for another MapReduce job. There's also a file format called sequence file. And sequence files are these packed binary files. So they store binary data types. They can store data other than text. So any arbitrary records that you have defined with a custom format, or if you've got blobs for JPEG images, or whatever else have you. So you would put these into a sequence file. And then you'd use the sequence file input format, which would read your keys and values in. And then you would actually have whatever data types you wanted as your mapper input types. And this supports compression by blocks and other good features to make sure that this can be read really fast. Finally, there's this sequence file as text input format. So that will read the sequence file, but it will just do the toString operation on both the key and the value. So you could use that with the mapper that expects some text input if that's what you wanted. Is there a plan for a format for an XML file with a specific schema? There is currently an XML file format, but it is very limited. What it expects is an XML document which contains some set of base records that are never nested inside themselves. And so it does the really naive thing of finding the start and end tag for that, and everything in there is just a text that gets shunted to you.
Might be a dumb question. How about like DOM parsers? Like for example, suppose you have nothing but web pages.
Currently, there is no DOM parsing format that I'm aware of. I'm sure lots of people would find that useful, though. All of these formats extend file input format, and so if you use this file input format's add input path when configuring your job conf, this will read all the files out of a specified directory and sends them to the mappers. You can, this has a single method that it uses to actually determine which files to read, though. So you could easily subclass file input format with your own format that does, say, looks for only files with a particular extension, or somebody, I believe, asked about how do we make sure that we don't redundantly execute over a data set if we're dumping things into a particular directory. So you could override this logic with your own logic that was pickier about which files it chose based on timestamps or file extension or other features of interest. And so this input format also has a method called getRecordReader, and this returns a record reader object. So theoretically, that could be used for capability multiplexing. An input format could return multiple record readers. In practice, there's a one-to-one correlation between input formats and record readers. So that text input format gives you this line record reader. Key value text input format, key value record reader, so on down the line. You could reuse these record readers, though, if you wrote a different input format that, like I said on the previous slide, was selecting individual files. You could still use the same record reader as one that you already know how to work with. And so this record reader object is what actually populates an object of the key type and an object of the value type and actually reads from the input stream for the file. So if you have a particularly unique file format to your organization, like say you have log files of a particular bizarre binary representation, you could write your own input format and your own record reader that knows how to read records out of this log representation, or some scientific apparatus that's got some weird instrumentation data, and you could read that directly into your own data types and send that all to your mappers.
In the record readers, there's a method called getPosition, getPos, and it says that it just says returns the correct position in the input. Now, earlier on you said you can scan and you can go back. Now, are these absolute byte counts or are these record counts? When you try to get the position, when you get the position, it doesn't say in the description, or is it up to you to decide if what you're getting is a record count or a position in some offset?
Boy, deep technical question about how the record reader get position method works. The shortest answer I can tell you is load the text input format class and find the line record reader and see what it does. And that would tell you whether it's bytes or records. In practice, I don't actually know that it really matters. The only thing that is actually used for, never mind. It's definitely bytes. And what it's used for is gauging a rough approximation of intermediate progress. Because it knows how long the split is in bytes. And therefore it can say, oh, I'm 80% done with this map task. In practice, however, if you always return 0, it would not semantically affect the program. Right, so as I said, by default, uncompressed files, or I should say files that are compressed with a splittable compression algorithm, or uncompressed files, get split into chunks. And by default, the chunk size is usually the same as the block size in the DFS. This is technically a free-floating parameter. So you can set that, this mapred mid split size is a parameter you can send to the job conf. And so you can control the split size if you wanted to. In practice, leaving this equal to the block size is probably your best bet. And so these record readers receive file and offset and length pairs, and that's what corresponds to an input split to define where the record reader should actually be doing its reading. So the third argument to that map function is called an output collector. And so this is what you use to actually get data to the reducers. So you call this output collector.collect method, it'll take your key and value and copy them off into a buffer elsewhere that it's using to assemble the data that it sends to reducers. So the output key value types can be different from the key value types as input. You just have to tell in the job conf what types to expect. So the fourth argument that we have is called a reporter. And this allows us to send some simple asynchronous feedback back to the job as a whole. So the most simple is there's this single status string that is globally defined and for a job. And any mapper can set the status string that it wants. So this is a really hacked out way of doing some very basic debugging if you wanted. If you were drilling down into a particular mapper or something, you could set that. There's also this notion of counters in Hadoop. So you might say that you're getting records of two different input types, and you just want to know what are A records, what are B records. And so you can define a custom counter for A's and a custom counter for B's. And each time you see one, you can increment that counter by 1. And it will assemble the counts that are coming up from all the different mappers into a single tally at the job tracker. And so when the job is over, you can say, OK, I processed 20 million A records and 30 million B records, or whatever else you feel is necessary.
This is interesting. So could you, in effect, like if you were looking for an anomaly or something like that, a huge data set, could you use the counters to say?
Sure, you can count. You could count malformed records.
But I mean, if you're just looking, so the second you found one, you could tell the job tracker, like, stop, we found one, or something.
The better way to do that would be to get a handle to the job object and explicitly kill the job.
Can you see the counters while it's running?
You can see the counters while the job is running, but they're unreliable. And the reason for that is because given speculative execution and the potentiality of map failure, it tracks how much was incremented to each counter by each task attempt. And so if a task attempt fails, it actually decrements that out of the counter. And so that when it reruns another attempt of the same task, it'll apply the new counters from the succeeding version. So the counters will bounce while the job is running. And then when the job is complete, it'll actually give you the final sums. So it's a really poor way of tracking progress.
Will it also tell you the sums of things that have dropped?
It will not tell you the sums of things that dropped. That data never happened because the task never happened because there was a successful attempt.
Yeah, I was thinking about collecting other kinds of data that aren't specific to the task, like the status of the machine, some keys or something.
If you've got other status that you want to collect, then the best thing to do is to actually open up some files and write that out on the side in your own channel. So the other final thing that this reporter does is it gives you back a handle to the input split if you want it. So you can get your input split, see what your file name is, etc. We've got mappers, we have reducers, we've got to get data between the two. And how do we know which reducer gets what? This is a process called partitioning and shuffling. Shuffling refers to the copying, partitioning refers to the dividing of inputs into reduce slots. So the partitioner interface, given a key and a value and the number of partitions, which is to say the number of reduce tasks, returns an integer defining which task that key and its value should go to. By default, it takes the hash code of the key object and sends it to key mod num partitions. So you could set the partitioner implementation to something separate. If you know something about the shape of your data, like you've got an awful lot of data that's going to hash the same way, then you could override this with a different partitioner implementation that is a little more intelligent. So finally, this goes to the reducer. And so here we get a key and an iterator of values, the output collector again, and a reporter. And so here we get a key and all of the values for that key. And remember, this values thing is actually returning the same object, but with different data inside. So in here, you'd do a for each loop over your iterator and actually do your reducing. So much like we used input formats and record readers, we've also got this output format and a record writer. So when you call output.collect from the reducer, it uses the output format to get a handle to where the file should be written and opens up a record writer that knows how to write your data types into the appropriate file. So by default, it calls toString on your key and value, puts a tab between them, and calls it a day. If you use the sequence file output format, it'll pack them into the binary file. You could write your own record format for that as well. There's also a null output format. Very commonly, people want to write to, say, 2 or more different output files, and they don't want the default file generated as well. So that's how you can sort of turn off this empty default file that would be created. So rather than calling output.collect, you could write the files yourself. So that's the Hadoop flow. You can override most of these components. So you can bolt your own logic in pretty much anywhere your data is involved.
Are you going to talk about using Hadoop with non-Java applications?
Yes.
Okay, good.
So you want to use a scripting language.
Oh, yeah, right.
Faster development time, easier to read, easier to debug. You might have a whole bunch of existing libraries that are all written in Python, and you've still got a whole lot of data, so you want to use Hadoop for it. Enter Hadoop streaming. So this allows you to interface MapReduce with any arbitrary program code and it uses standard in and standard out for your data flow. So you define a separate program for each of your mapper and your reducer. And the way this works is that the input key value pairs are presented to you with a key, a tab, a value, and a new line for each record. And so it all comes in as text. And you process this using whatever language your script is written in. And then you emit lines of the same form on standard out for the key, tab, value, new line for the key value pairs to send along to the reducer. Then the MapReduce engine picks that back up by reading the output pipe, does the sorting, does the shuffling, does the partitioning, and then fires off an instance of your reducer, which is a separate program, and sends data in the exact same format. And so you might get multiple lines with the same key in a row. So if your reducer has one key that has 20 values, you're going to get 20 lines with the same key and different values. And then you're going to get other lines with a different key and it's all different values, so on down the line.
If you have binary data, like images.
Yeah, so the thing is that your binary data would be in like a sequence file or something.
Yeah.
And the sequence file will read into the Java data type that you've defined to hold the record because it has to read out of the sequence file into something.
Okay, so you have to marshal that into your own language.
So you'd have to marshal it into a particular data type that you've defined to encapsulate the blob. It could just be as simple as just holding a byte stream.
Right.
And then you would then it will call toString. So your toString method should do something sensible like base64 encode it before it gets sent into your Python program or whatever else.
Okay, thanks.
As I understand the reduced task in Java, you can be guaranteed that you'll get one key for each call. So you can do, for example, given this a key value, a set of values, you can just sum them up, for example,
right,
and just write out the key. Whereas in streaming, tell me if this is true, you could get multiple keys. You actually have to sense if you're using the same key. You know what I mean?
So you have to sense when the key changes in streaming.
Right.
So
how do you? So what's the right way to do that? Because you maintain like a local hash table, or
parse the line, you memorize what the last key was. I mean, all of the values for all of the same values for a particular key will be presented together. So it'll say key 1, value 1, key 1, value 2, key 1, value 3, key 1, value 4, key 2, value 5, key 2, value 6. Yep. That's all there is to it. If you wanted a really simple mapper that just takes the key and a value and flips it around, you could write it in Python like this. Just read the line of input from standard in. When it's done, you're going to get an empty line, and that's how you know you're all done. And then strip the new line off the end of the line, split it on the first tab character to get the K and the V, and then print them out in reverse. There's an implicit new line on the end of the print statement. That's a simple streaming program you can write in Python to do some mapping. So the way that you launch these streaming jobs is there's a special jar that contains a job that represents streaming. So you'd pass arguments for this that select what programs to run for the mapper and the reducer, where the data is coming from, etc. You could also specify Java classes for the mapper and the reducer, although currently those must be inside Hadoop's internal library. So Hadoop comes with an identity mapper, for example, and you can use that just by saying org apache hadoop mapred lib identity mapper. But you can specify any arbitrary program command string to use for the mapper and the reducer. You can write your own scripts. You could also, identity mapper is cat. You can use WC to do some cheap summing. You could also use cut for field selection. You could write creative little awk scripts. Use your imagination. That's all I've got about streaming. There's some pointers to the wiki. That's what it is.
Well, what's the penalty? Because
What's the penalty? The penalty is you've got a bunch of extra copies of the data that have to go through because, of course, they're going to be in separate process spaces. So it's going to have to be, so if your data is in Java's process space, then that's going to be a copy to a kernel buffer followed by a copy back into this other process address space. Plus, you've got a context switch penalty every time.
So, in our installation, right, I was one of the first users of Hadoop, so I went pure Java, man. I want to do everything proper. And everybody else, of course, went streaming because it's fast and you can get up to speed really quickly. And of course, what's happened over time is that you do everything in streaming now. And what I'm trying to figure out, and I'm hoping to learn today, is does it make sense for our regular jobs to convert them back into Java so that they run faster, more efficiently, whatever?
I mean, you're definitely going to eliminate overhead by staying inside the single task, inside the JVM. So if there's a production job that's running relatively slowly, you might want to, and then the same job runs every day and it's mission critical that it completes within 30 minutes, then yeah, that's something you want to look at refactoring into Java. But developer time is expensive, as is machine time. So that's sort of the trade-off that you play with there. So that's the morning.